So now is about the time for us to apply what we've learned to some other field, and this is actually an application from physics, one that you may or may not have seen before. This is about our position function and velocity and the relationship between those and what it has to do with us in calculus, especially of higher order derivatives. So let me just motivate this discussion by saying, okay, Mr. Met fires his t-shirt gun almost straight upward to send some lucky fan a t-shirt in the bleacher seats. So what could we say about the position of this t-shirt after it gets fired from his gun? Let's say it's going almost straight up right here. Well, in physics, you may have learned that the position function is given as s of t. Well, s of t would be the horizontal position and the vertical position. Of course, there's when we fire at an angle uh, uh, for some object, we may have seen that at the initial position right here, there may be some horizontal component of the vector and some vertical component of the vector that goes along with that particular object being fired up in the air. And that object, its position, of course, is given by x, and its vertical position given by y, right? And there's a vertical y velocity and a horizontal y velocity. Well, okay, in this case, we're firing it almost straight up. So that means that, when Mr. Met fires off his cannonball T-shirt, we're only going to consider the vertical position, and we're going to let the horizontal position be 0 at that particular point. So we're not even worried about what happens as it goes side to side. We're going to look at the vertical position. So what was the vertical position function? It looked like this. The position function was the velocity, or the position of the final is equal to the initial position, vertically speaking, above the ground, plus the initial velocity in the y direction times time, plus 1/2 times the acceleration in the y direction times t squared. Now, if we're in free fall, what is that acceleration? Well, you may have learned that if it's just due to gravity, it's not a rocket-powered t-shirt, then we might say negative 9.881 meters per second, right? 9.8 meters 1 second squared. Now, there were a couple of velocity equations. There was one where you're given a v final, which was really just an abbreviation of the Pythagorean theorem. Since we're going straight up, we don't even have to ignore this. Here is our position function, our velocity function that we're interested. So there's actually a relationship between this position and this instantaneous velocity function from the world of calculus. And that's where we get these higher order derivatives. So here's our equation. Here's the way this works. We say, well, in this case, instead of y final, right, we're going to say that our position is all in terms of s, right? S is our y position. It's just a vertical fired up cannon, right? So s is equal to negative 1/2 gt squared plus the initial velocity. So instead of saying v initial, I'm replacing the I with a 0. So let I equal 0 at time 0, right? So the initial velocity and the initial position. Okay, and we could say it's either in 32 feet per second squared or 9.8 meters per second squared, depending on the initial velocity and how we want to frame this question. So here's a question. A Mr. Met t-shirt is fired upward from 1.5 meters above the ground at an initial velocity of 21 meters per second. The gravitational constant, we're going to say it's negative 9.8 meters per second squared. What is the velocity of the t-shirt after 1 second for when it's fired in the air? So here's where we're going to use our derivative. We learned previously that if we took the limit as delta t approached 0 of our position function s of t, so s of t plus delta t minus s of t divided by delta t, gave us that velocity, right? We said that would be our velocity equation at time t, right? And that is, in fact, the derivative of our original function. So if I was interested in finding the slope, well, let's set up our function. our initial position right here is 1.5 meters above the ground, and our initial velocity, v0, is 21 meters above the ground. So if I set up my equation, s of t will equal negative 1/2, well, it should be 1/2 times our acceleration, but 1/2 times our 9.8, I'm just going to round it to 9.8 meters per second squared times time squared, plus the initial velocity, that's 21 meters per second times time, plus the initial position, that's 1.5 meters. And so our position equation could be expressed this way. It would be negative 4.9 t squared plus 21t plus 1.5 meters. And so if we're interested in finding the velocity, what we're going to do is we're going to take the derivative of the position function to get it there, right? So our velocity is our derivative of our position function. And in this case, that ends up being negative 9.8 times t plus 21. Right? So if we were interested in finding the position at time t equals exactly 1 second, our velocity at that 1 second mark will be negative 9.8. Yeah, 9.8 times 1 plus 21. And that works out to be, let's see, 11, we're going to say 11.2. 11.2 meters per second. Okay. Well, it started out at 21 meters per second, and because it's going straight up in the air, it's slowing down. It did slow down to 11.2 meters per second. How about the acceleration? What could we say about acceleration? Well, acceleration, in the same way that we set up our velocity as being the change in position over change in time, acceleration is the change in velocity over change in time. And so we could say, well, if we took the limit as delta t approached 0 of our velocity function at t plus delta t minus the velocity at time t divided by delta t, and then we simplify that expression, we should find our derivative. V prime of t is equal to the acceleration at time t. So what would that be in this case? Well, in this case, it's actually really simple, because if we take our velocity function, v of t, which we expressed as negative 9.8t plus 21, and we took its derivative, v prime, we're going to get negative 9.8 times 1 plus 0, or negative 9.8. And so at t equals 1 second, our acceleration is, as we would expect, a constant negative 9.8. If it's in free fall, well, that's a constant acceleration. So that's exactly what we would expect to happen. And so it kind of verifies for us that if we are given a position function, when we take the second derivative, our derivative of s, right, our second derivative of position, which is our first derivative of velocity, is acceleration. Pretty cool.